Yesterday, after I took up the questions you guys had, we went and we did the Stairmaster Lab. You guys found out what your power was by using your mass and the amount of time it took you to run up a flight of stairs. Your work done is equal to mgh, because optimally, like, what you're doing to do work is you're causing your mass to rise a particular distance. You've got Harshan. Good morning. And then you figured out the amount of time it took you to go up those stairs. So the amount, your horsepower to raise you would then have been calculated way down here at the end of number 4, where you took your power in watts and converted it into horsepower. And I think Manuel, according to the numbers I saw yesterday, is our most powerful person at 1 point. What, Manuel?
If you're in space but not in space, if you can't hear noise, right? But if you're inside of space, you can't hear noise.
You need air. There has to be a medium for sound to travel through.
Exactly.
Answer my question though now. What was your horsepower? 1.6. 1.6-ish. 1.61. Okay, and I don't think anyone managed to exceed that. So congratulations, Manuel. You're the most powerful person in the class, apparently.
Well, you haven't done it, though.
It's not this year, but you're right. I have not done it. I should have done it yesterday, but I'm not. I'm going to move forward today. Riley and I should have done it the other day yesterday. How are work and power similar? What did you guys conclude? Completing this was your homework. What was, let's go through them, I guess, all 4 of these questions. What single variable determined who did the most work? Mass. Mass. Assuming you managed to do it in the same amount of time, the most massive person is going to do the most amount of work. Does the amount of work done by the student depend on how fast they climbed up the stairs? No. What was dependent on how fast they climbed the stairs? The power. How fast gives you the time, but what is dependent on the amount of time it takes you to climb the stairs? The power is what's dependent on the amount of time it takes you to climb the stairs. Does doing the most work mean you are going to be guaranteed the highest power output?
No, but in the most cases, it will mean that because the amount of work has more influence than amount of time.
But you got to answer the question the way it's posed. Does doing the most amount of work necessarily mean having the highest power output? The answer is?
Yes.
That's not what I'm asking. The question says, does the most amount of work necessarily mean having the highest power output? Yes or no? If you're saying most of the time, does that mean all of the time?
No.
Then the answer to this question is no. For the reason, Luis, that you're trying to explain, but you got to answer the question the way it's posed. The answer is no. Because even if someone is doing less work, if they're doing it substantially faster than you, they're going to have a higher power output than you are. But Luis then is going to argue that, well, usually this would be the case. And we don't actually even know if that's usually going to be the case. We'd have to do a lot more research to figure out if that's usually the case. You're presuming it to be the case. We don't know if that's how likely. We know if we can even say usually. And then you guys already calculate your horsepower. Work and power, how are they similar? How are they different? The difference is easy. Power depends on time. Work does not. And in this case, one of the similarities could be, well, they both depend on moving a mass. You can't have power and you can't have work done unless something has moved. So there's a few ways you could have answered this particular question. however you want to choose to answer that. So that was your homework. I'm assuming there are no questions. We just kind of talked it through. Flip ahead. Let's talk about the work energy theorem. So the work energy theorem is going to be given to us by a mathematical formula we've already looked at. So imagine a large rock inside a tall vacuum chamber. The rock is released at the top of the chamber and falls, accelerating at 9.8 meters per second squared. As it falls, what happens to its potential energy?
Potential energy decreases.
Why?
Because it's losing energy as it's falling and it's gaining kinetic energy.
Okay. So if we remember potential energy, and in this case, what kind of potential energy is it describing? Gravitational potential energy depends on some height above a reference frame, so or above a reference point rather. So we're calling height to be, we're calling the ground to be our zero. So as this thing drops, it's losing potential energy, turning that into kinetic energy. So as Connor's already said, what's happening to the kinetic energy? What's happening to the kinetic energy? It increases. Will any energy be lost? Or will all of the energy be changed from potential to kinetic energy?
Complete conversion.
It's going to be a complete. Why do you think it's going to be a complete conversion? Because it's in a vacuum, which means what?
No air resistance or any type of
Okay. So will any energy be lost? No. According to these gentlemen up at the front, there is no air resistance. So no energy lost. To what? What is air resistance going to do to pull energy out of the system?
It's going to break the fall a little bit up the rock, so its kinetic energy will decrease.
But what's it turning the energy into? Energy has to go somewhere. Because, we'll come back to this in a second, the law of conservation of energy says, chemists, we've seen the law of conservation of energy? We have not? Okay. The law of conservation of energy. There's a whole bunch of these conservation laws throughout physics. One of them is the law of conservation of energy. It states that no energy can be created or destroyed. So energy, if it can't be created, if it can't be destroyed, it can only be transformed from one form to another. So where would that, if there was air resistance, you guys already said we wouldn't be gaining as much kinetic energy. So where would the energy be leaving to? Be leaving in the form of heat. As an object falls, it heats up, which you guys don't necessarily, you guys perhaps have never seen, because the objects that you guys have dropped aren't dropping, far enough or fast enough to really be impacted by this.
Like something falling from space, though.
But something falling from space
Into our atmosphere.
into our atmosphere all of a sudden goes from a vacuum to experiencing a lot of air resistance. And we've seen this before, right? You guys have, I'm really hoping that you can tell me that you've seen this. We've all seen shooting stars, right? Or meteors. Hands up, you've seen a meteor? Okay. Some of you need to go spend some time this summer stargazing. The only reason you're seeing them is because they're exploding in our atmosphere because they're heating up due to the air resistance that's being impacted on them. It's melting and exploding these rocks as they enter our atmosphere, right? So they're losing energy in the form of heat as they fall. So how that's going to end up looking here, as far as the law of conservation of energy states, the mathematical implication here is that my energy initially must equal my energy at the end, according to the law of conservation of energy. This is restricted by what? in a more general sense. If my energy initial equals my energy final, this statement is restricted by something. So if we're talking about an object falling, let's say this large rock was not in a vacuum chamber, but it's really, really tall. We drop the thing. If all I'm looking at is the rock, is this a true statement? Is the energy of my rock at the beginning equal to the energy of the rock at the end? No. But if I zoom out and I look at the entirety of the vacuum chamber, because as this rock falls, it's going to heat up the air around it. If I look at the temperature of the air and the rock and all of that together, is this a true statement? Yeah, all of a sudden now it's a true statement, because the energy contained within that chamber at the beginning is equal to the energy at the end. At the beginning, all it was potential energy. At the end now, we've got potential energy. Sorry, at the end now, you've got an increase in thermal energy, which we're going to look at in a day or two, and we've got extra kinetic energy of the rock. So this is always a true statement, but it's restricted by, and the language we're going to use here is the scope of the system. And what I mean by the scope of the system is how narrowly you're looking at what's happening. On the scale of the universe, is all of the energy in the universe at the beginning equal to all of the energy in the universe at the end? If I'm looking at all of everything we know, has any energy lost? Does any energy escape out of everything we know? No, it's always there. So it's important to recognize that if energy is not conserved, that means your scope is too restrictive. You're looking too closely at something. If you zoom out a little bit, you'll find that lost energy. And that shows up like this. In real life, most situations involve air frictions or frictions of various kinds. Nothing is perfectly lubricated. Like you can have a roller coaster, but you're going to lose something between the rails and the track, for example. And so we say that some energy is lost. I want to put that lost into quotes because it's not lost. It just isn't in our object anymore. It doesn't belong to that object.
You can notice this by sound as well.
Sound is another great one. Yeah, absolutely. Use the object as heat usually and sound. Heat is a bigger, much larger suck of energy. Sound is very small. Sound's the one you notice more often because you don't have to touch it to hear it. But heat is the bigger, certainly the larger of the two. But yes, Luis is right. Certainly, they both have an impact. And we view this energy leaving the object as heat and sound as work done. Not by the object, but by the things that the object is interacting with. And in this case, what we're going to discover is that the work is actually going to be negative because it's lowering the energy of the object. Energy is negative work, means energy is leaving the object. And so to compensate for this, what we do is we rewrite the law of conservation of energy explicitly to include the fact that our object may lose energy to other factors, but we want to increase the scope just enough to compensate for that. And so what we do is we take our law of conservation of energy and we say that the energy that is present initially plus whatever is work done is going to be equal to the energy at the end. And work done, this can be a few things. It can be energy lost to heat or sound, or it can be energy gained. due to some sort of outside action. Instead of having that large rock just being dropped at the top of the vacuum chamber, maybe you give it a little push at the top. You're adding work in the form of some extra kinetic energy. So then if you give it a little push, all of a sudden now the energy at the end as that rock hits the ground in the vacuum chamber is going to be higher than what it started with. Why? Well, you added something to it. So this work term here compensates for someone outside of your scope either drawing energy out or putting energy in, depending on the context of the question. So as an example, we're going to look at this. This here is a classic roller coaster question. You're going to do a bunch of these over the course of the next 2 years, assuming you take Physics 12. We've got an object, a roller coaster cart. Let's put you in it. There you are. You survived. Somehow you got bigger, but that's okay. And this is our initial state. This is our ending state. What's happening as you ride the roller coaster? Let's assume that you are able to just barely crest this hill here, and then the snapshot in time happens. What are we going to see as far as the amount of energy that you have at this point right here?
You're almost hitting zero.
Let's effectively say that you are. In what form, though? What kind of energy is hitting zero?
Kinetic.
Your kinetic energy. So if we barely make the hill, that's the language there is implying that your kinetic energy, is it actually going to be zero? No. But can we practically say that your energy is zero? Like effectively? That's what I'm trying to argue. That's what we're going to do. So here we're going to say that kinetic energy is equal to zero. But what do you have here?
Lots of potential.
Lots of potential energy. So where are we measuring our potential energy relative to?
Like the bottom of the whatever you want to call it, and then the bottom of
Here? Okay. So let's add that in there. You're calling this height 0. I don't think it can't be ground. Why can't it be ground? Take a look at the rest of the picture. Why can't that be ground?
Oh, because it wouldn't stop.
Yeah, unless you're playing Roller Coaster Tycoon, you got a huge problem here. Right? Like, this is, we're calling this height 0, but it's important to recognize this is not ground level. But for the sake of the problem, I'm totally cool calling this our height 0 because it's all of this that's happening is going to be relative to this dip, our lowest point here. So that point right here, we've got a kinetic energy equals to 0, and we don't know what our value for potential energy is going to be, but we can assume that it's going to be what? It's going to be the maximum amount we're ever going to have. Absolutely. Potential energy is a maximum there. And we'll call this potential energy initial, and we'll call this kinetic energy initial. What can you tell me about the energies that we have down here at the bottom?
Kinetic energy will be at its max, and P will be at like 0.
The kinetic energy at this point is going to be at a max, and PE is going to be 0. If this thing is frictionless, what can you be more specific when you say KE is going to be its maximum? It's going to be equal to the potential energy initial, assuming if there's no friction. So as you fall here, your kinetic energy goes up, your potential energy goes down. As you rise up here, what's happening now?
Your kinetic energy goes down, your CE increases. That's not going to be the max of.
So what can you tell me about kinetic energy at this point and potential energy at this point? And min was 0. So my kinetic energy here is going to be greater than 0. Less than our whatever our max value is. And our potential energy final is going to be what's our potential energy going to be at this point?
Max of that though. It will be the same or greater than 0, but less than that.
How do you know? What is the determining, what has determined this to be true?
The distance above 0, the height.
Yeah, because our height, our final height is less than our initial height. There's all sorts of physics here that it goes into, designing roller coasters, right? As long as you start at your highest point, as long as no other loops, no other peaks are ever as tall as that first drop, you can do whatever you want. You can have barrel rolls going on in here, you can have loops. It doesn't matter what happens in the middle. As long as nothing exceeds what you started with, you should be fine, assuming that you're not losing a ton of friction and sound. Cool? Comments, questions, concerns? Okay, let's do a whole bunch of examples today then. Flip the page. Am I going to do all of these with you? There are 5. Are we going to do them all? Okay, so number 1. We've got a diver running and diving from the edge of a cliff into the water that is located 4 meters below. If she enters the water at 8 meters per second the instant she leaves the cliff, find the speed at which she enters. So this question sounds an awful lot like what? Sounds an awful lot like kinematics. We could do this using kinematics if we wanted to, because here's the problem. For some reason the water's green. This is the Olympics in Brazil. The water is green. For those of you who watched the Olympics in Brazil, this was a real problem. The water was green. We've got someone diving. We'll assume it starts as horizontally. He's moving. V is 8 meters per second. We know the mass of our diver is 56 kilograms. And we know this is 4 meters. This looks an awful lot like the projectile motion stuff that we ended kinematics with. And we could solve this if we wanted to using kinematics. How would we do it? if I wanted to solve kinematics? Can someone give us a quick walkthrough? Yeah. Which class are you coming from? Aren't you guys supposed, like, at this point, you're using computers every day. You bring your own? Well, you all should. Maybe we should just stop letting you use the cart. You bring your own. How would we solve this thing using kinematics? Who remembers? Manuel.
We can divide the horizontal motion and the vertical motion.
Right, you divide it into your x motion, your y motion. We'd say that there's some sort of horizontal velocity here is 8. The initial y velocity is going to be 0. The acceleration is going to be negative 9.8. The height that we're dropping is going to be 4. We can use this to find the time. Yada, yada, yada. We can use this to find the final velocity, blah, blah, blah. Or we could use energy. We can use the work energy theorem. To solve this problem instead. We know that the law of conservation of energy states that energy initial plus whatever work is done is going to be equal to energy at the end. This is not a energy, as we've already established, is a scalar, not a vector. Energy doesn't depend on which way you're going. So we don't have to do any breaking up here. We can just say, well, all of the energy that exists at the beginning plus whatever work is going to be done is equal to our energy at the end. So what kinds of energy now does she have at the beginning of the problem? She's going to have potential energy. What kind of potential energy? Gravitational potential energy. What else? What other kind of energy is she going to have? Question says, if she is moving at 8 meters per second the instant she leaves the cliff. So is she moving as she jumps? Yes, she's moving. So yes, we have kinetic energy. Basically, Connor, I was just asking you to commit. You said if she's moving, she'll have kinetic energy. Well, the question says she's moving. So does she have kinetic energy? Yes. Okay, so does the question allude to any work being done to either add to her or to remove energy from her?
There's no air resistance and this frictionless.
Yeah, the only friction that there's going to be would be the air, because we are told to find the speed at which she enters the water. So the instant before impact is what we're looking for. So is any work being done? No. And that is because there is no mention of air resistance. And typically for something like this, you wouldn't really acknowledge air resistance unless your diver was like friggin' huge or moving really, really fast. So what kind of energy is going to exist at the end of the jump? Kinetic energy is going to be there. I'm going to call this initial. We're going to call this kinetic energy final. Is there any other energy as she enters the water? As she enters the water.
Yeah.
We're calling this, we're going to call the water height 0. As she enters the water, she's hitting height 0. There's no potential energy there. So this is our work energy equation. Gravitational potential energy plus kinetic energy plus 0 is going to equal kinetic energy final. So now we can fill this thing in. The only sound that we would take into account here is if, like, she was moving so fast, she was whistling as she went through the air, like an artillery shell. because we're talking about the instant she enters the water, there has yet to be a splash. You don't hear the impact. We haven't heard an impact yet because there isn't an impact yet. This is the instant before impact. How fast is she going? So again, unless she's whistling as she shoots through the air, and not like, but like World War II shell screaming through the air kind of thing. There's no going to be any energy loss to sound. So we've got an MGH here plus a 1/2 mv initial squared, and that's going to equal 1/2 mv final squared. Let's look it over here. And now we can fill this all in. To make our life a little bit easier, does anyone notice something that we could do here first? Manuel? No, the kinetic energy doesn't cancel. We can't assume that the kinetic energy cancels.
Well, we can cancel the mass.
We could cancel all the masses because the mass exists in each term. There's no work term here. So because we could divide everything by mass if we wanted to. Does everyone see why? You know what? I'm just going to leave it in there because I'm not convinced everyone sees why. So let's leave our mass in there. Mass is 56 times 9.8 times her initial height plus 1/2 times her mass times her initial velocity. That's going to equal 1/2 times her mass times VF squared. That's what that expression is going to look like. So then how fast is she moving? Let me know when you got a value. You got a value? 11 point. Sweet. So she's moving at 11.9 meters per second as she impacts the water. Cool. Comments, questions, concerns about the process? That is the value that you're looking for. That's the same thing I got. So, cool. Love it.
There's a question that's like a normal velocity to reach the water, or is it a really fast one? Because I know you can die if you reach the water too fast.
This is a normal velocity. Like this makes sense, assuming that this makes sense. The problem here is that no diver is going to leave the cliff at 8 meters per second, because 8 meters per second is almost 30 kilometers per hour. So this is Usain Bolt running at a full sprint, jumping off a 4-meter high cliff. Yeah, this is salvageable.
I brought two laptops.
What class you coming from?
The science teacher told me.
The science teacher. You don't know his name? Is it your science teacher since the beginning of February?
Yeah.
You don't know his name. Is it Shapansky? That one. Okay, you had a classmate here 10 minutes ago, or 5, yeah. Why okay, whatever, yes. Why don't you all come down at once? Like, don't you all know you need a computer?
I just showed up.
You just showed up.
Yeah.
Like, for the first time since February?
No.
Oh, today. Okay. This late. Okay.
It's okay.
Okay, yes, you can steal a laptop. Well, borrow it, and then, I'll get it back from Shapansky later. Okay, number 2. A car of mass 1,500 kilograms has a velocity of 12 meters per second and accelerates to 25 meters per second. What is the work done? So, just like in our dynamics questions, we always started with F net equals ma. Now here we're dealing with this work energy stuff. We are always going to start with the work energy theorem. My energy initial plus whatever work is being done is going to equal to my energy at the end. And now we just got to analyze this thing to death. So what is actually happening here?
The car is traveling at one speed and then it accelerates to a new speed.
Okay. I have a car at 12 meters per second. And now my car initially was 12. Now finally, my car has a a velocity of 25 meters per second. The mass of the car is 1,500 kilograms. We want to find the work done. Well, there has to be work done, right? Because there's nothing else to increase my energy. It makes no mention of a changing height, so it's not like it's rolling down a hill gaining speed. You've just pushed the pedal down, and now we're just burning gas faster. Yeah?
Isn't a treadmill, it's not actually like going distance. So would that still count as work?
Yes, because there is still work being done. You got to careful when you apply what definition of work. So if the car is on the treadmill, is there any work being done by the car as a whole? The car's not going anywhere. So whatever force is being applied, Manuel, you could argue that no, well, actually on a treadmill. No, because technically it is still going somewhere. It is covering ground even though the ground is rolling away underneath it. So yes, there would still be work being done. But we're not looking at that. What we're looking at is the amount of work that goes into the system. Do you understand what I mean, Manuel?
Yeah.
So, but we're not looking at that. We're looking at the work that's going into the system to move those pistons faster to increase the speed from 12 to 25. So what kind of energy does this car have at the beginning? It's got kinetic energy because it's moving. Does it have any other form of energy? No. Work is being done. Work has to be done because nothing else is going to cause it to increase its velocity. And we know that there's kinetic energy there at the end. So let's go flush this out. 1/2 mv initial squared plus whatever work is going to be done is going to equal 1/2 mv final squared. Can't cancel masses now because there is no mass in my work term. So it's going to be 1/2 1,500 times 12 squared plus whatever work is done is going to equal 1/2 1,500 times 25 squared. What's the work being done? a value? No? What'd you get?
I don't know if it's right, but
That's
like
okay.
4.3
4.3 joules, that's it? That's a small number. That is different than what I got.
That's 17,850.
That is also different than what I got. Also different than what I got.
Yeah, okay. that's
360
what I
what? 360,750 joules. Yes, that is the value that I got.
got. How did you get that? Especially in math. I did math too, but
Do your math again. So the math, we're just solving for W, right? So it's going to be 1/2 times 1,500 times 25 squared minus this term right here. So this right here is 108,000 plus work is going to equal 468,750 is what this number is. So you're just going to take 468,750 minus the 108,000 that you got from this term. And you're going to find that the work done to do this is 360,750 joules. That's a lot of work.
oh, okay, yeah.
You see why if we didn't find this, you see why? Okay.
I calculated that.
No. I introduced my grade 9s to this morning.
Yes, you showed us.
I showed you. The problem is between the calculator and the chair. Okay, I want you guys to try, see what you can do. I want you to try number 3 on your own. For number 3, I want you to assume no energy loss to friction or sound. And I want you to try number 3 on your own. Set it up, just like we've been setting up the previous 2. Reason your way through it. See what you can do with number 3. The value you're looking for is between 12 and 13. See what you can come up with. Oh, yeah, sure. Oh, you haven't had it this whole time. Yeah, I didn't want to. Let's put down that. Yeah, what you need. Start with the expression that we were starting with now. Energy initial with the work energy theorem. Energy initial plus work equals energy final. Careful. That's not the statement.
You don't need to know it. You can't be putting that, right?
You cannot analyze this from that.
Is that a true statement? What does it tell you with the top there?
No. Yes. You can do better than that though, because I'm telling you what the height is. And I'm telling you what the velocity is too. So is kinetic energy equal to 0 at the top of that graph? You can't analyze this one the same way to the example, because the example I gave you very specific criteria. It's just barely making it over the top. You didn't know what the height was, but now I give you a height and tell you what the velocity is. You have to use that information to change our assumptions a little bit.
No, I'm not supposed to know the math.
You did?
What did you say this answer? N equals 13.
Write out the whole expression, please. I'll give you the mass, it'll probably cancel out. Are we still making forward progress, or do you guys want a hand? Want to see something with this? Okay. Still want to play with it? Okay. This is good. Oh, I told you to ignore. Assume no energy is lost through friction and sound. So that's going to get rid of one of these terms. Work. Because nothing's pulling energy out of the system. Sorry? That is that's what that work term represents. It's really handy if you wrote if you wrote things down. I'll show you what I mean. That work term, Manuel, does represent what's happening. That work term is energy lost to heat and sound, or energy gained due to outside action. That is what that work term represents. Working on your math is more important than paying attention to what I'm trying to teach you. Confused with what? Okay. How can you cross off potential energy? Because you have some height above, it gives you a height above the ground. So yes, you're moving, but you're also going to have kinetic or potential energy up here, because you're going to drop. So there needs to be a potential energy term here. There is not going to be a work term, because the work, it represents energy lost. And I told you at the beginning of the question, I put a star here and I said, assume no energy is lost to friction or something. And that's going to equal this state here, because you're up on a hill again, you've got potential energy again. But you're also still going to have some kinetic energy, because the height of this hill is less than this one. So you haven't converted all of it back into potential energy, that's still going to be there. So you're going to have potential kinetic at the beginning, you're going to have potential kinetic at the end, because I told you there's more friction in that. So we're going to subtract that 117.6 over 198 minus 117.6. And you're going to divide that by 25. And then you're going to, square root. No, you're good, Colin. That's correct. Because the square root of 160 is going to be just like 12 and a half. So yeah, no, you're good. Okay, let's take a look. We've got 15 minutes left in class, so I do want to do a couple more with you guys before I release you. So let's take a look at what this thing actually ends up looking like. The problem that I'm seeing, at least at the beginning, that a whole bunch of you were coming up with was you were looking at this, the example I did before, and you're saying, okay, well, this must be the case. But the example I gave you before, this guy here, was a thought exercise. So some of the things that I gave you here may no longer be true. The one little tweak that I gave you here compared to what we talked about before was I gave you an initial velocity here at the top of that peak. So if I'm going to start with, sorry? So if I start with my work energy theorem, assuming that this is what I'm going to call 0, what kind of energy do I have at the peak here? Potential and kinetic. I have motion, and I am some height above 0. So there's going to be potential, gravitational potential, and there's going to be kinetic. The question I gave you, I told you to assume no energy lost to friction or sound. So is there any work being done by anything on this roller coaster? No, that's going to be 0 because of this statement right here. And then at the end, there's going to be potential energy, gravitational final, plus, as Luis already said, kinetic energy final there. So I'm going to get mgh initial plus 1/2 mv initial squared is going to equal mgh final plus 1/2 mv final squared. There is no work term, and every one of these terms has mass. So the interesting result here is it doesn't actually matter how many people are in that roller coaster. Which is why there is no weight restriction on roller coasters at theme parks. The only restriction they have on roller coasters at theme parks is height, because they don't want you to get decapitated. And they don't want you to fall out due to the lap belt. It doesn't matter how heavy you are, which is beautiful. So we're going to get 9.8 times 20 plus 1/2, 2 squared, is going to equal, good morning, Mr. Radnai, plus 1/2 V final squared. If you run that through, and the mistake that I saw a few of you make is one that I regularly make. At the end, when you're solving for V final here, you're going to have to square root because you don't want V final squared. You want that to be V final. That's a mistake I make all the time. What you're looking for here is a value of 12.68, actually, meters per second. Hey, what's going on?
Hey, just a quick update. After yesterday's meeting, the last week was, scheduled the assessment week.
Can you make the 12 meter height 0, and then you can get rid of your potential?
Ooh, could we have made this height 0? Absolutely, we could have. And if that becomes height 0, then this height is now what? That's going to be 8. And then that's going to change this into potential energy initial plus kinetic energy initial is going to equal kinetic energy finally. Absolutely, you could do that, 100%. Because the where you set 0 is totally arbitrary. Absolutely. The math will work out exactly the same. You should get 12.68.
Yep.
Questions, comments, concerns? Okay. Flip the page. Question is, do I want to give you some of this to work on and then finish some of this stuff later? What do I want to do here with you? What happened Thursday? What are we talking about?
It's easy concept.
Sorry, what are we talking about?
How's it significant?
Oh, chemistry. I don't know nothing about a chemistry test. Okay, I'm going to give you some time. I'm going to give you a couple questions for homework. I'm going to give you some time to practice this now. We will finish the rest of this up tomorrow because I do want to give you some class time to play with this a little bit here. I want you guys to do the following questions. I don't know where there should be answers at the bottom of this. I don't know where they went.
Where are they?
They have been cut off. I don't know why. I will give them to you.
Mr. Rudolph?
1 second. What is going on here? Something is very weird. Oh, that's what's happening here. Okay, so I want you guys to scribble out question number 10. Question number 10 is awful.
Oh, yeah.
Question number 10 is awful. Oh, dang, this is the wrong page. Shoot. Okay.
Whoa.
Okay, here's what I want you to do. I want you to do question number 4. I want you to, well, let's do 3, let's do 4. Let's do 5. Let's do 8.
158?
Yes.
Very cool.
3, 4, 5, and 8. And we will pick this or the rest of this up tomorrow.